recording, right?
Appear to have audio.
Okay, so people in this class don't tend to do spectacular on the first test, and that's largely because you come from different disciplines. But I've taught this class now for 7 years. There's usually pretty steady progress as the semester goes on. So, like they say in The Hitchhiker's Guide to the Galaxy, don't panic. But I just copied some students' answers here that I gave full credit to, and we'll go over this. And I want to add some motivation while I'm talking about this. So the important thing, since I'm asking about gas reservoirs, is each initial condition should have been to the right of the critical point, like this student did. Okay? Anything to the left of the critical point is what type of reservoir?
Oil.
It's an oil reservoir. So if you had an initial point on your reservoir that was left of the critical point, you were not answering this question, because I'm only talking about gas. And I think it's very important to make a distinction between these three reservoirs, and I'm going to go into that after I look at this page. So I'm looking for vertical lines here for path of depletion, because the temperature doesn't change in the reservoir. It's isothermal, okay? But as you come up the wellbore, it changes temperature and pressure. You can pick up your test over here. So, and some people kind of drew two line segments, but it's a curve. If you look back at the PowerPoints that are loaded at our D2L site, it's a curve, okay? So if you ever have to sketch these again, draw it like this student did and draw curves. So it didn't really matter where your initial pressure was, as long as it wasn't inside the phase envelope. And I don't think a single student did that. So you can't have an initial conditions in a two-phase region, because in geological time, they would separate, and then you'd have a gas cap and an oil cap. So condensate reservoir, also known as a retrograde condensate reservoir, will, during the path of depletion, will go into the phase envelope. And what does that mean? What happens?
Liquids form up.
Liquid dropout. Okay. Now, what does that do to the liquid production rate?
Increases.
The what?
Increases.
I can't hear what you're saying.
Increases.
No, it doesn't increase the liquid production rate if it drops out in the reservoir. See, the well stream gas is carrying the richer part of the fluid. But once it goes below the dew point, that richer part of the fluid drops out. It becomes two phases. The only thing still flowing into the reservoir is the leaner fractions of the gas. So what we produce at the surface will not be a rich gas with a lot of liquids. The liquids will drop out. And so now we're producing a drier gas. So we're losing liquids in a retrograde condensate reservoir. Now, if your permeability is high enough, and this is a true story from my professional career, the state of Wyoming, if you show that you have retrograde condensate and you're high enough permeability, they'll make you shut in the reservoir until you instigate a pressure maintenance project. Because the state of Wyoming, you come up and get your test over here, guys. The state of Wyoming doesn't want to lose the revenue on that liquid. They're going to make you operate this reservoir correctly. Now, if the reservoir isn't permeable enough, it's impossible to maintain a pressure maintenance project. But the idea of a pressure maintenance project is to keep it above the dew point, to inject nitrogen, CO2, lean gas, anything to keep it above it, and sweep the rich gas toward the wellbore so that you get maximum liquid production. I want to stay with condensate reservoirs, and I'm going to see if I can pull up a relative permeability curve here on the internet. Is there not even a search bar? And here's a good one right here. Might be there. The point I really would like to make on this is this right here. No oil flows. Now, we have, oh, this is a water oil. Pretend this is gas oil. We have a residual oil saturation. In a retrograde condensate reservoir, what is the initial oil saturation in the reservoir?
0?
0. Okay. So 1 minus that, if this was the gas saturation instead of the water saturation, your saturation starts increasing. This is the liquid that's dropping out. It's starting to increase. But you notice that in all porous media, there's a residual oil saturation. So until it gets to this point, which it may never get to, that oil that drops out never flows. It's lost. And with oil being over $100 a barrel and gas being less than $4 an MCF, it's the liquids that are valuable, even in a gas reservoir. So it doesn't matter if you're going to work for an exploration and production company, upstream, or a midstream company. You're always looking at reserves. That's why we'll be looking at that again when we look at our P/Z. We're always interested in reserves because let's say I'm a midstream company and I'm going to process liquids. Okay? I'm going to be taking some kind of well stream of a rich gas from a well and I'm going to process liquids. Well, initially, maybe it's making 100 barrels per million cubic feet of gas, and I do a P/Z and I say it's got 24 BCF, but will it hit a dew point? Because if it doesn't hit a dew point, I can design all that recoverable gas, some recovery factor times the gas in place, to process the liquid. So I may design my plant one way. But if I have a dew point reservoir, I may only have a short life, but maybe 6 months, 8 months where I produce that much liquid, and then it's gonna produce a lot less liquid. And if I build a plant to handle that much liquid over a long life, I'm gonna waste a lot of money. So it doesn't matter what aspect of the industry you're in, you have to know the difference between the reservoirs that are being produced. Whether you're talking about your internal reserves, if you're an exploration and production company, or even if you're a midstream pipeline processing engineer, because the reserves can make all your calculations wrong because you've over-anticipated the amount of liquid production. So anytime we have a retrograde condensate reservoir, we're going to lose a lot of liquid production. Okay, the rich gas reservoir is kind of my favorite. From a reservoir engineering standpoint, do I ever enter into a two-phase region in the reservoir? No. So my relative permeability to my liquid, or to my single-phase flow is always 1, okay? Now, notice, let me back up, because I didn't really complete the condensate reservoir thing. As my liquid drops out and no longer flows, if that isn't bad enough, it clogs the pore spaces, so I get less gas. Anytime you have two phases, if I sum one phase and the other phase together, the relative permeability of both this and this at any saturation, it's always less than 1. So I always have less permeability open to flow when I have two phases present, two modal phases present. Do you have a question?
That's it.
Okay, not yet. Okay, so again, I think it's critical that we know the difference between these 3 different kinds of reservoirs. Okay, again, now I'm moving on to rich gas again. Rich gas I like because it's going to be single phase in the reservoir, and I still get liquids. I still get that valuable commodity liquids. If I somehow knew what the composition, what the phase envelope was of my prospects, I would want a prospect that would come down just like that. Why would that be better than this prospect right here?
More liquid.
Well, the more liquids, the more closer I move to that phase envelope, the more liquids, okay? So maybe I'm getting 150 barrels per million instead of 50 barrels per million by drawing that next line in there. That's the ideal situation. Plus, in a permeable reservoir, I'm going to get maybe 80% recovery. So I'm not only going to get 80% recovery of my gas, I'm going to get 80% of my recovery of my liquids. This is a phenomenal number. In an oil reservoir, we typically get 10% of the liquids because we always go through the bubble point. We're trapped over there to the left of the critical point. There's no chance of missing the phase envelope. Look, see that? If we're in the oil region, there's no chance that we're going to miss the bubble point, the saturation pressure. We're always going to go into a two-phase region in an oil reservoir. In a gas reservoir, we have a chance of missing it. So yeah, that's the ideal situation. Get a lot of liquids and get a high recovery. Okay? So the last case is dry gas, and this person kind of drew the line so it misses it, but typically it kind of stops right about here. It wasn't important to go all that way down, but they definitely got the idea. So the only problem with the dry gas, it has the advantages that it's always going to be single phase flow. If it's a permeable reservoir, I'm going to get 80% recovery, but it's not worth very much at $3.80 an MCF. Okay? So rich gas reservoirs, in my opinion, are the most favorable. If I was looking at a portfolio of middle maturity properties that I might want to purchase, I would be looking for rich gas reservoirs, because these condensate reservoirs are probably going to be overvalued because they're going to show a lot of liquid production rate currently. But if I know that it's a dew point reservoir and I'm going to have liquid dropout, I could have a drastic situation. I could spend way too much for that reservoir. So not only is this a midstream, upstream decision, it's also a mergers and acquisition decision to know these basic fundamentals of these 3 different kinds of gas reservoirs. Any questions? Okay, that problem I gave 6 points. Basically, a point for each line. You see that? A depletion line and a path of production line. And I skipped the first one. Most of you got the first one right, but the approximation that we're going to use all semester long for System compressibility is gas compressibility times gas saturation. I gave some people partial credit for that, but that was with 2 points. Now, I think I got this up in here. Okay, so this was that second one. Now, let's see, let's take a picture here. So I can mark it up. I don't know why it floats on me. Okay. I think there was one student that talked about pressure gradient, how we could get gas gradient, gas gravity, and I gave some credit for that one, but that was, but primarily what I was looking for is getting the actual data for the first, second, and third stage. Individual gravities from each separator is known. API to liquid is measured. You didn't have to comment about the impurities. We have to have the GOR and the gas gravity from each stage, okay? Then we can actually do basically a molecular balance. There's some correlations built into that because the relationship between API and molecular weight of the oil is a correlation. But if it was exact, then it would be a mole balance on the produced stream to get the molecular weight of the gas gravity, or which is related to the gas gravity by the molecular weight of air. Okay? And then the second stage, and I underline it here, is that it is a correlation, and we have to know the separator pressure and temperature. Now, if we know the separator temperature and pressure, then we can calculate that BEQ and GPA. And so I pretty much gave you full credit if you use BEQ and GPA, but what I really was looking for is that you had to know the primary separator GOR, and you had to know the primary separator pressure and temperature that it operates. And that's what's required to be able to use that correlation. And in the field, that's what we normally do, especially when we're just spot checking some situations. I can go out there to the field, check the separator pressure and temperature, ask the pumper what the gas separator gas gravity is. That's always known because we're always selling it on a daily basis. And then I can immediately use that correlation and calculate the well stream gas gravity. I could even generate a phase envelope and see whether I had a condensate reservoir or not. Okay, so I gave 4 points for that. I gave a lot of partial credit, but basically I was looking for 2 points for knowing all the gravities and the GORs, and 2 points for having the separator temperature and pressure. But I gave a lot of partial credit to use BEQ. I don't think I need to copy this over. So this person got everything right. I guess I didn't. I don't know why. Maybe it's just because I'm mean, but I like students to know how to do long division. So I think exhibited here is a good example of all the calculations you need in order to get the formation volume factor. okay? So it's just the real gas law. I gave you Z. You didn't have to use the gas gravity, you didn't have to use a fluid properties correlation. If you had a computer, you would have just looked up B sub G based on pressure, temperature, and its impurities, and its gas gravity, or basically its concentration. But knowing a Z, you can calculate a formation volume factor. Okay, PSC over P times Z times T over TSC. You can derive, you should be able to derive, just like we did when we first did our, that one homework problem with the cylinder, and we calculated Z's. We gotta get it, we have to have know the fundamentals of the real gas law. So calculating a gas formation volume factor represents the ability to understand the real gas law. And then all you really need to know after that is the volumetric equation for gas in place. And you should be able to know how to convert what we get from a log, the height, the porosity, and the saturation data, with an area, and the fluid property, your formation volume factor, and get your gas that you'd sell in standard cubic feet or 1,000 standard cubic feet in terms of a reservoir volume or a reservoir area. This is your very fundamental reservoir engineering type volumetric equation. And I'm going to show two P over Z's. This one was real good because it had the right numbers. So it's important to know that when you're at zero pressure along the gas produced line, that you have your original gas in place. In other words, the x-intercept is your gas in place, and the y-intercept is P over Zi. That's fundamental. But I was also looking for, because I gave 4 points for this problem, I was also looking for the idea that you can get recovery. So it's one thing to know how much gas is in place, and of course what we normally do is produce the well for a while, measure the pressure, and calculate a P over Z. And then calculate another P over Z, and then make some kind of extrapolation of that line as the way it's normally done. In a permeable reservoir, when we can shut in a well and rapidly get an initial pressure. Now, we're in chapter 6 now, and we're going to be doing pressure buildups. The idea of a pressure buildup is you produce the well for a while, the rates decline, and also the pressure declines. I'm going to get another color here. Well, Y still got that. And then you shut in the well, okay? So now rate versus time. I'm using lowercase q for rate. And at the same time, if I'm measuring pressure, let's get purple. The pressure may decline a little bit, like this. But what happens here to the pressure? It goes back up. And it usually has a nice little curve like that. So then I may go back on production. Has it reached average reservoir pressure? No. But we're going to be looking in chapter 6 at ways to extrapolate the pressure buildup data to average reservoir pressures. So we don't have to shut in a well long enough and infinite amount of time that would be required to find out average reservoir pressure. We'll utilize chapter 6 techniques to use whether we got radial flow or linear flow to build that data up and find out what the average reservoir pressure is. So either from a static pressure or from a buildup pressure, we gather this information and then we plot it versus the cumulative gas production to that time. And then we can extrapolate and see what our in-place hydrocarbons are. If we know from our logs, our height and our porosity and our saturations, what will that tell me? This will be a really good test question. Huh?
You know your banner pressure, you get your drainage area.
You get your drainage area, right. If you know your gas in place from material balance, that's what this is a material balance, and you know your cross-sectional volume from a log, then the only unknown in your SGVHA is A, because your log gives you SGVH. And this is assumed, well, of course, your Y-intercept here is all you really need to calculate your formation volume factor. So this is frequently done. A new well, I've logged it, I produced it for a while, I capture a couple more pressures, I know the gas in place, I can now back calculate the drainage area. So initially, maybe I just assumed, remember when we were making up numbers in class, I just assumed it was draining 640 acres, and so we calculated the gas in place for 640 acres. This way, I can actually calculate the real drainage area, utilizing material balance. So we're going to always kind of use material balance. Petrophysics is where I get my porosity. We're not going to actually practice in petrophysics, but anytime we have porosities and saturations and heights, that's coming from well log data.
Do you still have to assume either an abandonment pressure or a recovery factor though?
In order to get your,
Drainage rate?
no.
There you go.
That's an add-on. That's an add-on, okay? This extrapolation tells you gas in place. Boom. Your SGPH, okay? So I have that number before I calculate anything, see that? And if I have logs, I have SGPH. And if I have initial pressure, I've got formation volume factor and composition. So the only unknown there is area. You don't need recovery for this. But if I'm in design mode and I'm in contract mode, I have to know how much gas I'm going to process and how much gas I'm going to sell. And I'm going to have contracts. So it's the recoverable gas in place that I'm also interested in. Now, just with the original gas in place, like I just explained, we can calculate drainage area. And of course, we may want to know that because if we drill another well in the same area, it's only going to be 2 straws in the same soils. If we want to get more reserves, we're going to have to drill outside that drainage area. But a recoverable or economic ultimate recovery, G sub P sub ultimate, is what we're going to probably use for our contracts and our design calculations. So I'm trying to give you the motivation why this kind of stuff's important. And I'm launching chapter 6 here too, because we're going to be able to get extrapolated pressures from our pressure buildups. So far, we won't have a good drawdown. I don't think I had any other ones. Was there? That's the end of my PDF. Okay, I'll save that. So you'll get this ongoing PowerPoint, which I'll hang before the next test. Okay, let's get back to work. I think this is where we left it. Has everybody got this spreadsheet?
How did you distribute the marks for question 3? The CGI and
Which question is it?
3, the OGIF and CGI? 4, isn't it?
I think it's 4 points, 2 points for OGIP and 2 points for VGI. You may have given some partial credit.
Do we have to get the final number correct?
Yes. I didn't see anybody that got either, some people got 3.32 times 10 to the minus third, or they got a number so far removed from that there was no partial credit. But maybe if they set up the problem right, I sometimes gave partial credit if they set up the problem right, but just didn't calculate it right.
Yeah, because I did everything, but I get 0, except for the calculation.
Yeah, you wouldn't have gotten credit for just setting it. You wouldn't have gotten full credit. You had to be able,
You got 0.
you had to be able to do long division in my classes, and multiplication.
I think I did it correct, but I did not convert the temperature.
Oh, there's a lot of people that forgot to add 460 to the reservoir temperature. That would have cost you. You know, in industry, you can't make that mistake. I'm preparing you for industry. I'm not really lenient on those things. I gave partial credit for setting up the equation.
No, you get me 0.
I'll be glad to take a look at it. If you have the right equation for B sub G or for original gas in place, I should have given you partial credit, but I'll look at it. You can give it to me if we take a break or at the end of the hour. Okay. But no, to get full credit, you had to get the numbers. 3 significant digits. Even though, if anybody would have gotten it to 2 significant digits, I would have given them full credit. But people either got it to 3 significant digits, or they didn't get it at all. Okay, does everybody have this much information? I think the only thing we tried to do in the last class is calculate a gas gravity, isn't that right? It's 0.64 is what we got, and we looked at errors. I forgot what error we looked at. This looks like the B sub G error. And yes, and then I think we, Gene, you're the one that helped me with that one. We set a lower limit rather than solve. And then we got a reasonable number for B sub G.
Did you calculate the SG or did we just enter that?
SG would then be CT over CG.
So we did calculate.
And I get CG using the gas gravity that we back calculated from the volumetrics. Because compressibility and Z factors utilize the same equation of state. The one in our software is the Benedict Webb Rubin 7th order equation of state. It's very accurate. Remember that C sub G is just 1 over P minus 1 over Z dZ dP. So if you're getting your Z's right, then the gas gravity that I use to get my formation volume factor, so then that same Z subfunction dZ dP should be accurate and calculate my compressibility. So I'm calculating gas compressibility, since gas compressibility times gas saturation is total system compressibility, I can divide the 2 compressibilities and back calculate a gas saturation. This wouldn't be done in industry, but we're doing this because the textbook didn't give us a gas gravity. You wouldn't normally calculate gas saturations this way because you wouldn't be given a total system compressibility. You would calculate gas saturation from logs, 1 minus SW, and then you get gas compressibility like I just did from fluid properties, and then you get a C T, SGCG. You'd never use this procedure. I'm using this procedure because the textbook doesn't give me fluid gravities on a lot of these problems, and so we're modeling it. We're trying to be a little bit slicker than what the textbook really had us do. But I don't like the idea that the textbook's given us CT. Where'd you get that from? We would normally get it from the gas saturation times the gas compressibility. The gas compressibility would have been a fluid property, function of composition, temperature, pressure, and impurities. So I'm kind of making up for what the textbook didn't put in there.
Were we given the gas gravity?
No,
I don't know.
you just have a brain lapse here for us. You see how accurate that number is?
Yeah.
We used goal-seek. We actually didn't use goal-seek because goal-seek failed us. We used solver. And we set the tolerance of 10 to the minus 6. And we try to get that number right there, which is the relative error between the B sub G given and the B sub G we would calculate as a function of gas gravity. So we use solver.
Did you use solver for this?
Let's just do it again. Let's change this gas gravity to 0.8, okay? Then my relative error becomes pretty high, right? Now let's use solver. Where is it?
I think we have to install it again. Add in.
I gotta add it again? That's right, because I'm on this computer. We're gonna get good at this. So, I would have liked to have done a minimum for that cell L8. Remember which cell I want. I want K8. I want that to be, I would like to say minimum, but it didn't work. But if I set it to a small tolerance by changing F9, wow, I like that. It blinks. It's actually F9. So then I solve. Is that the same number I started the class with, 0.642? Was it, wasn't 0.68, was it?
I used the minimum it worked.
You did?
0.65, yeah. I got 0.65.
See, oh, you know what, I just did the wrong thing here. This is 1e minus 6. I want to, okay, K8, the value of K8. Oh, I see. You got to type that in by changing F9. Okay, so let's use goal C. Not goal C, but a minimum. Set K8 to a minimum by changing F9. See, I get 0. For some reason, solver didn't work for me. Keep losing it. So anyway, I end up with 0.642. And my gas saturation then becomes 65%. I think that's the way I started doing switch. Okay, does that help you?
Yeah, it's getting wrong now, we'll figure it out.
Okay. Again, this is not typically what you would be doing in industry, where I'm mad the textbook doesn't give me the gas gravity. But it's also smart and studious to learn how to model data. We're modeling the formation volume factor. They told us what it is, and they also told me the reservoir temperature and pressure that it's at, so I'm figuring out what gas gravity. I've also got to assume that all the impurities are 0 here. Okay. And if I want to carry this one homework problem to the teeth, you know, to the very limit, typically I can get a radius of investigation and I can get gas in place. And I want to know the gas saturation to do that. So usually I would be given the porosity and the gas saturation, but I'd never be given the total system compressibility. That'd be for the engineer to calculate that, SGCG. Okay, I think now we're ready to do a slope and a perm and a skim. And I spent a little bit of the last class period talking about what skim was. Wherever it is on my slide, right here. So, does everybody remember what skin is? Near wellbore damage. Or improvement if the skin happens to be calculated as negative. Positive skin is damage, negative skin is bad. Now, here's the textbook plot of our data, and I want to explain why they didn't select. I mean, you could have come up, if you're just looking for a straight line, why didn't they select this data?
Because it's in the early time period.
What about the time period?
Middle time you have to take.
Well, how do I know that the data they selected is middle time region, and the data I just selected is not middle time region?
2 degree slope,
Huh?
by 9 degree slope.
I think I started with the last
Before-
point.
The early time region will, when you plot it, you will get unit slope until you deviate from unit slope, then you.
Although, in this situation, it's a long-term drawdown, because isn't this daily data? Maybe it's hourly data. The concept of the word middle usually means avoid the wellbore storage data and avoid the boundary dominated effect data. That's why it's called in the middle. But if there is no wellbore storage data, you start with middle time data, right? And usually wellbore storage data drastically is different than middle time region data. I'm going to ask you one more time, why isn't that red interpretation just as good as the textbook's interpretation? And do we have the wherewithal to figure that out?
Are you looking for an answer different from what you just said?
Yeah, well, you'd have to read ahead a little bit, but later on in this chapter, we're going to do semi-log derivatives. The derivative of the data will be a horizontal line when we're in the middle time region. So the textbook kind of works us into that, but I'm going to try to put everything that's in the textbook in this first problem.
So what you're saying is we're looking for the linear region, basically, of this plot.
But wouldn't you agree there's two linear regions?
Well, clearly not, because if you take the derivative and you don't have a horizontal line out here,
Well,
it's not
that's
linear.
Yeah, but we haven't done the derivative, have we?
Well, just looking at it, you can see it trends downward, so you're not going to have a constant. You're going to have a constant derivative.
Are you saying, looking at this data, you can tell me that this has a horizontal derivative and this doesn't have a horizontal derivative?
I can say just based on the trend line that's already there and how well it fits the data in the middle time region, it makes it really easy to see that the stuff in the early time region is trending down.
It doesn't seem that easy to me.
Okay.
Even if it's trending down, could it be trending down linearly?
No.
As that market having its own, having a set.
Yeah, I haven't got a straight hedge, but if it's a straight, but let's just do the work. 'Cause I think that we're gonna always want to do the work, and so I'm gonna put some things in here. So we gotta learn how, this is delta P over Q, but for all intents and purposes, this is like the pressure. So we're gonna do it like a dPdt. Now, even though this is a variable rate, variable pressure problem, we're gonna do this, we're gonna use the superposition that we did back on 6.1 and do it and redo this problem even one more time. So I'm gonna call this, and we're doing this horrible piece of A, which is linear to pseudo pressure. And normally I just put one cell down. So your dP and it's a semi-log derivative. So we use Ln, and it's over time, and Ln, I could do Ln of 4.8 minus the Ln of 2.4, but everybody knows the log of A minus the log of B is the log of A divided by B. Okay, now I missed this. Put it in the formula. So this is, although we'll call this derivative, we have to know that this is actually, we call it a semi-log. Derivative.
That is ln of what? I mean the natural log of what?
I'm sorry, what?
I mean, can you go back?
dy d log of x.
Okay, the time. Okay.
Yeah.
I'm getting a different result. Is it 8.3 minus 7.8 bracket divided by natural log open bracket by?
I know, this will help. Is that better? Remind me to zoom in, because I know that I keep forgetting that Kaltura has about 1/4 the resolution that Tegrity had. And I taught for 5 years with Tegrity, and this is the first year we're using this cheap knockoff called Kaltura. And so you gotta remind me to zoom in. Okay, I'm ready to throw this data on my graph. I think I can just do it with a copy paste. And it's a much smaller number, so let's put it on our secondary y-axis. And there's our derivative. Now, the data I like here, see that, I like purple, I'm working with purple today. The data I really like is right here, see that? From 10, and I should have done a little bit better job here. Incidentally, I really like it when they put inside tick marks.
Dr. Carr, can you show us how to create a new y-axis?
I sure can. I right-click the data and say format, and I went from primary to secondary. And now I got a little bit better font. And I got I've got inside tick marks so I can determine. So that, again, the data I really like here is when this is horizontal. And that's between 10 and 20, 30, we'll call it 35 here. That's horizontal. Okay, I don't like those first 3 points, and that's what the author did. Remember, he kicked out the early time data. But I'm not a huge fan of this late time data either. Now, that could be, if you take too small of a time interval, that could be noise. We're going to play with this. We're going to play with this. This doesn't really have any effect, but I could, right now I am plotting my first derivative at my first data point. I really should plot it in the middle, or if I plot it at the second one. But see, it doesn't change the relative value. It may change a little bit which I do. But I mean, I could even add a column and plot this at the average. These numbers. Again, it won't change the flavor of my plot, it just moves it over a little bit. I'd say that last plot I made is slightly more accurate for selecting the right data. Now, if I think this is noise, I can open up my derivative. So this is average P, this is average T. T's a P average. And that's for this plot. The other thing I sometimes do is I'll use 3 of these. See, you see I'm capturing a bigger time, I'll have less noise. And let's put that on here. I'm going to use this. And I'm gonna use this because it's at that midpoint. And you can see, I still like, I'm gonna do a rollover here. I still like just after 10 hours to 33 hours, okay? That's my favorite data, using a derivative qualifier here, 10 to 33. We'll call it that data right there. That's the data I like the best. Now let's look at their plot. I think they had a semi-long plot, didn't they? Time and hours, 0, 1, that's 10. See, I would tend to actually use slightly different data than they did. But I'm not done yet. But this gives you an idea how we do this. So now I want to do a slope. I'm going to do my own number. And I want to know the slope of this line, then we'll put it on there. So slope, that's a nice little function, known y's, comma, known x's, except for it's a log of my time, because it's a semi-log straight line. I need to get my textbook open. Let's see if they got a slope. Anybody have any idea what page we're on? 120. 120? Example 6.2, right? Here we go. So they got a slope of 1.09 psi per cycle, and see, I got a little bit steeper slope. I think I could probably get their same number if I chose their array. They took it from about the same starting point, but they went to 31.
Why did you choose the numbers you did?
I'll answer that question as soon as I type these two numbers in. Okay, 1.1 is the slope, 1.1, 1.09. So I'm matching what they're getting for slope. Okay, your question again is?
Why did you choose the numbers that you chose, like for
The highlighted numbers?
yeah.
Because 10 to 33 is where I had a horizontal line on my derivative.
Okay.
You see, a semi-log derivative is going to be, a semi-log derivative of 0 is going to be a semi-log straight line. So if I'm looking at the data, I can eyeball and maybe get a straight line here or a straight line there. But the acid test of where the straight line is going to be is where the semi-log derivative is equal to 0, or it is horizontal. Yes?
Please repeat the slope, stay very calculate the slope. We're not getting the same answer.
My slope or their slope?
Yours.
My slope? You want to look at the calculation?
Yeah.
So remember I highlighted that. I highlighted that data because that's where my derivative was horizontal. And I'm using log base 10 because it was the difference between chapter 6 and chapter 9.
The yellow will not be x values?
Huh?
The yellow will not be x values?
Yeah.
Why?
Yeah. The slope, function prompts for known y's first and then known x's second. And you can see I have a logarithm for my x's. I'm taking the log.
You're doing
You said you're taking the log.
I could have calculated the log of time and then putting those numbers in, but you see up here in my formula line, you see where I just highlighted the word log?
Okay.
It allows that.
Oh, it's not natural. It's 10 log.
I don't like to have a lot of extra columns in my spreadsheet. Remember, I live for the fewest number of keystrokes. Okay, everybody happy? I got my slope and I got their slope. Mine is based on, I just call it P prime. And theirs. Lee is the our text.
You said yours was based on P prime? I thought our P prime was the column.
This is P prime,
Yeah.
okay? It's horizontal from here to here. So I want to use that data,
Oh, okay, that makes sense. Okay.
all right? Okay, I'm ready to calculate perm. What equation are we going to use for perm here? Skin.
These are your points, these are your x's.
Since we're using apparent pressures, remember this is this convoluted thing the textbook likes, so the units. Equals 162.6. Now, we're going to use the B sub G that they gave us in the textbook, not the one I calculated in reservoir cubic feet per standard cubic feet, because they're using oil field or oil reservoir permeability equation adapted for gas. So I'm going to use this reservoir barrels. Viscosity is the same in oil and gas, it's in centipoise. Divided by my slope. Let's put theirs in first. And divided by my age. 23 feet. Okay, using the Lee slope, I get 124. The textbook got 0.13. All right? Let's go on with the Lee slope and get skin. Perm's easy, skin's a lot of work. We should be able to get this 7.8 PSI per MSCF per day as the intercept at t of 1 hour. Okay, so back here I have slope, I also need intercept. I'm not sure why I got these numbers here. And remember, I just like to change the spelling. I'm going to change the spelling from slope to intercept. And using their analysis, I get 7721, and they got 834. They cut off more of the early time data. Let's try to match their data a little bit better. Their slope doesn't have nearly as much early time data. It actually starts about here. And I think that's a little bit closer, 113, and so I'm going to do the same thing for their intercept. I'm going to cut off all the data that I would normally use. Incidentally, we're just beginning with the fight here. We're going to take this to a whole different level. 7862, they're still getting a lot larger number. At 1 hour, am I doing something wrong? The intercept on this graph of my slope at 1 hour is about a little less than 8, 7.8. I'm getting 7.5. I don't know how we're getting over 8. No, they're not. 7.8. I'm doing something. Oh yeah, 7.8. Yeah, we're all getting 7.8. This 8.34 threw me off. 7.8. Although I'm getting a slightly smaller number with my analysis based on pressure derivative selection of my data points. Okay, so now we're ready to calculate a skin using a different equation. And we're going to get 4.8. Skin is equal to 1.151 times in the braces, 1 over the slope. I'm using the lean numbers. Their slope times the intercept. 1 hour. Remember, well test units are hours, and we only use log base 10. Well, except for that derivative. Minus the log of the term that I calculated over the quantity 5 times viscosity times CT times RW squared. That's a wellbore radius. You guys probably already forgot that. That's the denominator. Now I close my log function, and then I think I add something, 3.2. And then close that. And I got 5.2. I got 4.8.
Can you zoom that in, please?
Pardon?
Can you zoom in on your,
Skin?
yes,
U average, CT average. Let me get this number so I can read it. Use prosody, RW squared. I don't know why I'm not closer to 4.8 using their number. very different numbers on this analysis, but I'm just kind of showing. I'm now going to get my numbers by changing which ones I grab. Instead of grabbing 1.046, I'm going to grab that. And instead of grabbing their slope intercept, I'm going to grab my slope intercept and my perm. And so I've kind of bracketed their skin of 4.8 with some data that's a little earlier and some data that's a little later, just to kind of show some sensitivity there. Let's all catch up to that point.
What did you use for the Q in the formula?
What Q? Oh, we plotted delta P over Q. See, we're actually Q varies, but we plotted delta P, which is a constant here. And then so the Q is actually in my plotting variables. That's why we have a little bit of a specialized equation here.
Which will be used for that?
Oh, it's the intercept of delta P over Q. It's the intercept. It's delta P over Q intercept. I'm plotting delta P over Q. I want it at 1 hour. And since my time units are hours on my plot, log of 1 is 0, so it's my intercept. Delta P over Q at 1 hour is my intercept, because log of 1 is 0.
Can you go back to the scan?
What?
The scan equation?
One over the slope times the intercept, delta P over Q is at 1 hour, minus the log of K over phi mu C sub T R W squared. Close my denominator, close my log, and add 3.23.
Did you calculate lead, slope, and intercept, or did you use any of those numbers?
I just picked my own data array. I could try to do a little bit better job. I could try to see exactly what was the first data point. It looks like here's 1 hour, he didn't use that. I don't think he uses 10 hours or 12 or 15. It looks like the data on his line start at T equals 30 hours. Do you see that? Let's try to match that. So his data starts at, well, that's about what I did. You see, I started at 38. I can move that up to maybe 1 data point for both the slope and the intercept. I gotta be consistent. Whatever straight line I have, I gotta use both that slope and the intercept. That's my best guess of what the textbook used. And that slope and intercept gives me perm of 132 and a skin of 5.1. And no, here we go. Now we're getting close. Maybe not. Where's my example? Oh, I thought I was there, but I wasn't. Yeah, we're not at 6.3 yet. Just write down their numbers. 6.3. actually got. I can't match their numbers exactly. I'm very close. My number using what I think they use as a slope, to two significant digits, I'm getting the exact same number. I can't quite match using the same slope exactly what they're getting per scheme. And let's see, delta PA. Oh, yeah, they gave us PA on PA. Or did we calculate this? No, we used their numbers. I'm not sure why I'm getting a slightly different number than 4.8 for my scan. That's not my biggest concern right now. When we're doing the sound.
What did they get?
I told you, they got 4.8.
4.8, and you got 4.8 as well.
No, I got 5.1 using what I think they use for their interpretation of slope and intercept.
I got 4.9.
Okay, now also I could hardwire their slope and intercept. Their
4.8.
Their slope is 109, and their intercept is 7.8. So, if I use those numbers, I get 4.8. I'm going to control Z, get rid of that.
I used new results and I got 4.8.
You got 4.3.
4.8.
You got 4.8. Yeah, you can get 4.8 using their numbers for slope of 1.09.
No, using your
1.05?
using the slope as 1.223 and the intercept as 7.58.
Yeah, for that I get a perm of 0.113, which is, let me get these all on equal footing, which is 11 versus 13 and 13. And I get a skin. Using my slope and intercept in my perm, I get a slightly smaller damaged area.
I get 4.9 if I use. I did too.
Using these numbers right here,
Yeah. And the perm was.
what do you get for perm?
4.1.
Okay, and you get a different skin.
4.9.
These are given viscosity and total compressibility average, 40% RW. You sure you squared RW?
Yeah.
Maybe I did. I did.
Yeah, I think you did. So I can see.
Okay, my slope and intercept. Now, also, maybe I got more significant digits. I'm actually using the equation, slope and intercept. But you should get, I don't know why you get a number different than 3. I don't know how both of you are getting numbers.
But I'm getting 3.3, exactly using the same number as 2.3.
So no one can get the same number that I can get.
I do.
Who does? Okay.
Can you go back to the range, please? Like, maybe that is where the confusion
Yeah.
is coming from.
My slope and intercept,
Yeah, that range.
yeah, is based on that highlighted from 9.6 hours to 33.
I mean the one from the textbook.
The
What you are zooming from.
textbook is one data point overlap, and then all the rest of the data. Mine is the highlighted data. So like I first drew, when I started the problem, I showed that there was kind of an earlier straight line with a steeper slope. So we're just looking at the subtle differences there. And I haven't even started what I really want to show. these equations are for a well that's produced at constant rate. And we're using an approximation of reciprocal rate. Okay? This whole technique is an approximation. I don't know how our textbook starts the paragraph here on 6.1. Okay, but it doesn't really give us too much comment, but we have the wherewithal to do a better analysis. I'm going to start with our data. You know what, I'm going to keep all this, I'm going to move a copy, and put it right next to it, because I want to do it different. This is 6.2. So this is 6.2.2. This is the way I'm going to redo it. And I'm going to insert some columns here. And you might remember in 6.1 we use superposition. Okay, we have a rate time function. Remember super radial? That when the rates change and the pressures change, we can use the rate time data and then the actual pressure, although we use pseudo pressure. Pressure function was, the pressure function's the same. Let me zoom in, you guys forgot to remind me. The pressure function's the same. It's PI minus the current pressure, which is always going to be the same for a current problem. There's no change in the bottom hole flowing pressure, over Q. So the pressure function's the same. Well, we had a rate time function given that first zero. It's always a little bit of a misleading thing. We use all the times and rate changes to that point in time. We can use the same function, super radial. Okay, let's use it. Let's see if we get even a different answer. And we want to do the semi-log analysis to see if we got a better selection of the data. So this is just super radial. The way it has to be anchored, I like to start down, equals, super, radial. Okay, it wants my time array, and I gotta remember to anchor the first time, so I F4. See, I'm on line 9, but I always want it all the times up to that point. So I'm anchoring A6 to A9. I'm gonna do the same thing for the rates. I don't know why I put these things. So I want all the rates up to that point. So I'm gonna F4 the B6. And it's going to be a logarithmic function automatically. And if I want to compare it to these numbers, I would just say equals 10 to that. And you can see for the very first point, it's going to be exactly the same because it doesn't do anything with one point. But as time goes on, that 9.6 hours becomes 10.3 hours. That 38 becomes 41.6 hours, and by the time I get to the end of my test, I've added 15, 16 hours onto my test. Using the same superposition function we used with example 6.1. So this is super. Log of T, and this is super T, 2.4 hours. I've added these two columns here. Okay, again, the 2.4 is not going to change for the first one because it's a summation function. I don't want to grab the first one because it'll be confusing. I'm going to grab one down in the middle.
Okay.
It uses all the rate time history to that point. So I anchor line 6 for both the rate and the time history. Once I don't know, there's no way to do it on my first one because, but I can copy it back. And when I copy it up, it looks like this. Absolute A6 to A6, absolute B6 to B6. It's saying, let's analyze this as a transient pressure analysis. And since the rate varied, and transient pressure analysis assumes the rate's constant, it's going to correct each rate time data for the rate history. As covered in the textbook. Right here, given any variable rate time history, shown right here, okay? Given any rate time history, we can use, oh, I do that all the time. I gotta remember to use the page down. We can use this equation right here and come up and plot, normalize our pressures, delta P over Q, and have this summation function that starts with the first rate time and goes to the nth rate time. So you use all the rate time history to that point, and it corrects the variable rate history as if it was produced at constant rate. And then I think when we calculate perm, we have to use the rates are built in. Okay.
What was the second column, super log?
After that,
Yes.
I just took 10 to that because the log has already been taken, so it's the log of time. So if I want to plot it on a semi-log data to compare it to the other data, I'm going to take 10 to it. That, oops. And it emphasizes that when there's only one data point, you can't change it. And if this rate was exactly the same as that rate, then this 4.8 would be 4.8 also. It only will change that number if the rates change. Okay, so now I have a new time. I don't actually have to do that, but I think it's more fun. So I am going to copy my delta PA over Q onto my plot. Wherever it is. Way over here now. And where did it go? Oh, it's right on top of the other one because it assumed the same x-axis. But now I'm going to change it. And now I actually have two, for some reason I lost, this is a secondary, no I didn't. Maybe, oh, I know what. Format data series assumes, now we're in good shape. When you copy paste in Excel onto graphs, data onto graphs, it assumes the axis of the previous paste. So I had to change it back to secondary axis. Okay, so now if I just look at my data, it's almost the same. In fact, the first data point has to be exactly the same, because remember, my 2.4 didn't change. But then my data changes a little bit. Now, let's do our derivative on our adjusted data. Is this getting complicated enough for you yet?
Yeah.
I just soon stay with one data set. What the book tends to do is keep changing data sets to show new procedures and new things. I just soon work everything we can.
When I change my other one to secondary, it flips the other one back.
Well, just make sure, to get this secondary, just format data series and make sure it's secondary.
Two that are in line
Both of
should be
these two should
primary.
be primary.
Okay.
So now I'm going to look at my derivative. I feel like I've got an improved data set. Let's see if I improved my derivative. So I'm going to do a couple of more. Let's see, what is this? So that's, let me get, which one is this? Let's add 2 right here. Let's get an average. My column E, I want to have 4 3 times because I always want it to be E. And I've changed my time from 2.4 to this new 2.4. This is the slightly smooth one. This is the second variable, the standard one I applied. That one's guaranteed to be about the same. And right now, I can't tell any significant digits. Oh, there's some difference. Okay, now, let's put this second one on. And of course, it'll show up on the primary axis until I adjust it. Look at that. Not much change. Seems to have corrected a little, it took a teeny bit of the noise out. Took a teeny bit of noise out. Okay, let's calculate permanent skin. Or let's decide what our best data is. I'd still say 9.6. I think I got the best data set, but let's see. I know that my superposition should give me a slightly different slope. So I'm going to keep the lead data, but I'm going to change mine based on pseudo pressure and superposition. So now instead of using 9.6 to 33.6, I'm going to use 10.3 to 36.4. And likewise for my intercept. So I just changed my slope and intercept, and that's gonna change my permanency. And let's see if that's any different than, I'm gonna flash back to my other page, 114 and 38. Slightly change it. I'm gonna copy paste these absolutely. So using superposition, I made a subtle change from 113 to 114, and a subtle change from 37 to 38. I think these are my best numbers. I augmented my test to use superposition. It doesn't make a big difference on this analysis right here because my approximation was fairly good anyway. I had smoothly declining rates. If I would have had drastically variable rates, the superposition would have been rigorously required. Okay, we ready to move on? Kind of beat that to death.
What was the last thing you did real quick?
I copy pasted my previous results from the other spreadsheet.
Okay.
Remember, I copy pasted spreadsheets so that I didn't have to have a new column. So I just copy pasted the old data in. And so, if no one knows these, I'm thinking 0.11 millidarcies is better than not using superposition or using a different, or using the second to the next straight line. And using the textbook, I would have probably gotten a higher skin, although using their slope, I'm getting 5.1. But definitely, the textbook analysis is telling me that there's more damage than I believe there is shown in the data. And somehow, I feel like if we really kind of beat these things to death, that we'll get a little bit understanding that we just kind of raced through them. Okay, the next thing I want to do is I want to calculate the amount of reservoir I investigated. And see, I don't think it's covered in our textbook prior to example 6.1 and 6.2. I think we have to jump down, or maybe it's up here. I take that back. There's our pseudo pressure. Where is our wellbore storage, radius of investigation? Right here. I'm going to copy paste this over. I have to cut this in half. That's pretty readable, isn't it? As we produce the well, the area from which fluid is drained increases. We're talking about a radial situation. So here's time 1, here's time 2, and here's time 3. Okay? Radial situation, we keep increasing the amount of reservoir we're seeing. Did we see a boundary in this example? My middle time reaching specialist. We didn't see a boundary. We see a sharp kick. And although we seem to have somewhat of a noisy derivative there, there's nothing to indicate that we saw a boundary. So the only thing we're going to do here for our time is, if we saw a boundary, we'd use that time, but otherwise we just use the last time measured on the test. We just want to see what we investigated, how much reservoir. The air moisture fluid is drained and the pressure transient moves further out into the reservoir. Defined as the point of formation of okay, so this is the equation we're going to use. Later on, we'll use this for a buildup. We're not looking at a buildup, we're looking at a drawdown. We're producing the well, we're drawing it down, we're drawing the wellbore pressure down, producing it. So let's use this equation right here. So you grab it from here. And I set up your template to do this. Okay, hopefully that is equation 6.13. It's a drawdown, so it's actually 6.12. I did a typo. Did I give you this spreadsheet, right? Okay, it should be 6.12 instead of 6.13. 6.13 is a buildup, so we're using 6.12. We're not going to worry about this TCDA of 1. We're just going to calculate one radius investigation using this equation. So let's calculate it. Let's use what we think is the best numbers. I think it's my perm. 0.11 millidarcies. This becomes sketchy. What do we use for time? Typically, the engineers I talk to use real time, 216. You see, if you use my superposition time, I'd come up with a larger number. That's just for the analysis of linearizing the fact that I ran a constant, I didn't run an actual constant rate test, but I had a variable rate. So I'm going to use real time, 216 hours. If I use the 231.8, it would give me a fictitiously larger area. KT divided by 948. Now let's open a parenthesis. 948 times porosity times viscosity average times total system compressibility. And I need 2 parens. I need one to close that and open. I didn't start with the paren. I'm going to do that now. Go to the end, and I take the whole paren and raise it to 25. And that gives me my radius of investigation in feet. Again, the example problem in our textbook didn't do this calculation, but they'll supplementally do it in other equations. I want us to get used to doing everything we possibly can glean from any test analysis the best way we can.
ability degree?
Pardon?
What probability degree?
I use the highlighted numbers in yellow. Mine's based on,
Is it based on its probability?
so here, I'll just highlight it here. Let me zoom in to everything I need to do here. I use the 0.11 millidarcies.
My skin was 3.7 after I
It
did.
doesn't use that, it doesn't use skin in this equation. My number is actually 0.114. So you can see, it's easy to get perm. In fact, it's hard to get perm wrong, even if you pick the wrong middle time region, which I think the textbook did. You're so close to the same answer, but then when you start looking at the intercept of the wrong straight line, it has a bigger effect on skin. In any area you have, it's going to have, actually doesn't have a bigger area on perm because you're going to take the square root of perm. So you reduce the area when you're calculating that area, not area, that error when you're calculating radius of investigation. Yeah.
So when we put these skins, the skin equations in our PA,
You can?
is the correct way for this one to call it non-Darcy?
I have told you that we're probably not ever going to look at non-Darcy flow. So I don't use the non-Darcy flow.
It's called variable rate.
Yes, but I worry a little bit. I mean, in my BB, I do have a skin equation for variable rate and also for buildup and also for constant rate drawdown, constant rate buildup. There's about 3 or 4 different skin equations in the tables. So I don't tend to, in this class, try to enforce you to use those. Because if you're going to do this type of test and you have your computer available to you, you just go to copy paste this page, put in different data. You'd have the equation for this type of test. You can do whatever you want to.
Well, I'm just trying to distinguish that it's a different equation. You know, what would you call it if you were to call, you have 2 skin equations, what would you call the one we just used?
It's modified because the first term is not,
It doesn't have B's, G's, one of them, so.
your standard, I'm trying to find the table now. Your standard skin equation will have a first term that looks like that. P sub I minus P sub 1 hour over M. Okay? Now, our intercept, we plotted delta P and got an intercept, so that's been replaced. It's no, it doesn't even show up on this table.
So it's the
It
same.
only shows up only in the example section.
Okay, yeah, I got it.
So it gets kind of confusing. You'd have to build a really long table, that term right there, and then we use it, I think a different first term on the example 6.1. So, and also we're using adjusted variables on this problem, so ours should look like that. This is table 6.1. Let's see, I think it gets continued. And now the other thing is, it's PI minus P sub 1 hour over the slope on a drawdown, and on a buildup, it's P sub 1 hour minus PWF on a buildup. It's that first term that you have to be extremely careful with by the test design. You'll see that your equation for perms may look exactly the same. but your, what you're using for your intercept depends upon your plotting variables. Because if you're using delta P over Q as your plotting variable, then that's gonna be different than plotting just pressure. It's gonna be different on a billet and different on the drum. I hope that totally confused you. I'm just kidding. Okay. Now, let's just go a little bit further with our radius of investigation. Here's another thing that we're gonna frequently calculate is apparent wellbore radius. We have damage. Is our apparent wellbore radius gonna be smaller or larger? Smaller. If we had a negative skin, would our apparent wellbore radius be smaller or larger?
Larger.
Yep. Okay, so we have an equation for that. It's really easy. Apparent wellbore radius is your actual wellbore radius times e to the minus s. So apparent wellbore radius, I'm going to put my symbol in here too, RWA. And we'll use this because we'll find out it's real convenient, because whenever it's asking for radius, you don't see skin in the equation, you can always replace RW with RWA and not worry about the fact that the equation didn't have skin in it. Equals wellbore radius 0.365 feet times EXP to the minus skin. I'm going to use my skin, 3.8. Remember they had a larger skin. So I shrunk my wellbore considerably. And I'll jump ahead. I think in my power, no, let's see, where did I have that? I don't think I put it in the PowerPoint anywhere yet. At some point in time, I flashed up some dimensionless variables. And when there is no skin in those dimensionless variables, there's an RW term. So when we ever see an RW in a dimensionless variable, we'll know to use RWA. So again, this particular problem didn't have us go and calculate everything that we could calculate, because they think that their strategy is just learn the two more important things you can get test by test and look at different tests. But I want to get everything again. Now, the manager walks in and says, I just see you completed the test. How much gas in place did you look at? I'm not going to call it original gas in place. How about investigated? How about GIP? I'm making this up. How much gas in place did I investigate? So we have a radius that we investigated, right? So there's our area term. We have an SGPH, and I think we have a B sub G average, but we haven't calculated a B sub GI. And we can't calculate a B sub GI with the data they gave us because they didn't give us a gas gravity. But now that we've calculated a gas gravity, we can calculate a B sub GI. So that's what I'm going to calculate first. And we have gas B sub G given pressure 4650, reservoir temperature of 200, gas gravity that we had to determine. See, I couldn't have gone to this level if I wouldn't have determined the gas gravity. And we're giving it these numbers for our impurities, and we're not forgetting to scroll down and getting the last one in. Now we have a B sub G. Now, am I going to say gas in place equals 43560 SGPH over B sub G, or am I going to do something different?
You have to calculate area from the radius of investigation.
Or I can just leave the 43560 out. Why convert my radius to acres and then go backwards and go from acres to feet? Okay? So my area, remember, everything's really in cubic feet. Okay? So my area is equal to what? Pi r squared.
Yeah.
But you had the right idea. You would have gotten the right answer going your way. But I would have used 43560 twice. Right? So I got square feet now. Multiplied by height, I got cubic feet. Multiply it by porosity, and I got cubic feet of pore volume. And multiply it by the gas saturation, and I got hydrocarbon pore volume. Right? And then take the whole thing and divide it by formation volume factor, and I got standard hydrocarbon volume in what units?
SCF.
So let's divide it by 1,000, because that's what we sell gas by, right? I'm gonna put a comma. It's not a huge amount, you know. It's only a 216-hour test, right? A 10-day test. In 10 days, I proved up 77 million MCF. Not a commercial reservoir yet, because if I take that and divide it by 26, it's only 0.078 BCF. I haven't really proved out the commercial reservoir. You got to have at least a BCF to get a commercial reservoir.
Can you please go back with the GIP? I just want to see the formula.
I'm sorry, what?
The GIP investigated. I just want to see the Q.
Okay, it's pi times 215 squared times the height, that gives me cubic feet,
Okay.
times the porosity gives me pore volume of cubic feet, times the gas saturation gives me the hydrocarbon pore volume in cubic feet, which is how much gas I have in the ground. Divided by B sub G, that gives me how much gas I have at the surface.
There's 1,000 there.
Hmm?
There's 1,000 there. You divide it by 1,000.
Oh, yeah, and then I divide it by 1,000 to get MCF. Okay, I think this is a good time to take a break. I'm going to switch over to here, hit pause. Durations move. Okay. So I'm going to copy this data over to the spreadsheet that we're working on. And I think I'll not use 622, but 62. And first of all, I want to move a copy. And there's just so many things that are the same in these problems. We'll call this 6.3. And now I'll come back to my PowerPoint. I'm gonna grab this first. And we'll get rid of some of this stuff. And zoom in. Oh, I did that over the other one, but that's all right. Paste. Now we're doing 6.3. And I'm in a copy of 6.2, so I'm going to change some things. Here we have a constant rate. This is standard drawdown. So we're going to use this rate. I don't have any place to put it right now. I'll put it here after SG. Q is 40,000 MCFD. Industry just usually uses MCFD. It's obviously more correct to use MSCFD, standard cubic feet a day. But most of industry drops the S. Okay, porosity is now 10%, so I'm going to change 14% to 10%. Temperature is now 200 degrees. It was 200 degrees for the last one. Total system compressibility is 112 times 10 to the 6. Here's a big difference. Remember on the last problem, they used an average pressure equal to the arithmetic average of the last final flowing and initial. Here on this problem, they're going to run the average pressure. So when it says CT average, that means at initial pressure, 4290. Now, one of the reasons they ran an arithmetic average of the flowing pressure and the average pressure is they were producing a constant bottom hole flowing pressure. But here, we're producing a constant rate, and our bottom hole flowing pressure is constantly changing. So, those are some small innuendos that H is 40. Now, they're telling us that the water saturation is 25%, so I'm going to hardwire in that the gas saturation is what? 75%. And they're going to tell me that Z is 0.92, and they don't tell me the gas gravity. So how about we use that Z. They didn't tell us the B's and G. I'm trying to leave all the columns and rows intact so that if I copy and paste that radius of investigation or something like that over here, it'd be good. So I'm trying to squeeze stuff in.
Dr. Callard?
Here.
Dr. Callard, there are more parameters on the next page.
Okay. Okay.
It's page 122 and 123.
All right. I'm still going to start adding on down here. ZI. Is 0.9. Oop. What in the world they got there? They got centipoise after Z. That's not right, but 0.92 is a typical Z value. Where's this more data? Oh, I see. B sub G, this stuff right here. Good catch. we've got all this stuff in here. So they're saying the B sub G average is 0.7163 reservoir barrels per MCF. RW is 0.3. Oh, they told us the gas gravity. And they told us that the gas viscosity is 0.0254. Okay, let's do some checks. What would I get for ZI? At 4,200, 200 degrees, 0.85, and 0 impurities. Not forgetting to scroll down to get H2S. I get 0.89. Let's see what I get for B sub G. Oh, I know. They're using a P average of 4290, not the average of that. They don't have a PWF. It changes. Let's get rid of that column, not make any more mistakes. Now I only have a 4% error. See how copying the spreadsheet over, helpful B sub G average, 71639 calculated, and then in reservoir cubic feet, it's that, I'm calculating that at 4% error. I'm gonna have to go with their gas gravity because they gave it to me, but I'm getting a pretty big discrepancy between what I would get for ZI and what they got for ZI.
But I got a zero.
Huh?
I got the 0.92.
You got 0.92
Yeah,
calculated
yeah,
at 4290?
yeah.
200 gas gravity is 0.85 and 0 impurities. I'm getting 0.89.
That's what I'm getting.
Very 93.
Huh? Yeah.
I got point.
But they're telling us that it's 0.92. But there's some kind of typo here because they got a center place. Let's just ignore it. Okay. CG. CT would be my fluid property calculated CG times their given gas saturation. I'd get a CT of that. That gives me a relative error on CT of that, 11%. Okay, I'm using their gas gravity, which we're going to just stick with, just to kind of get an idea of what we are. I'm getting a 4% error on their Z factor and 11% error on their compressibility. Okay, now I'm going to put in the time data. I just happen to have this already worked from the previous year. Here's my hours. And I'm going to be putting in pressure. Of course, everything's going to go to heck here in a second. Okay. And they're gonna do this in PA analysis, and we're gonna start dropping PA. I don't wanna do any more PAs anymore. The pseudo pressure. We'll find that we will not use exactly the same augmented oil equation, we'll use the gas equation. So I'm just gonna get a start here, and I'll let you guys try to finish this up. Let's do, I'll just keep you for a few more minutes. Let's calculate pseudo pressure. MOP. At each pressure, 4290. Relative. Temperature, absolute. Gas gravity, absolute. Impurities, absolute. Not forgetting to get hydrogen sulfide. Okay, we're going to work with pseudo pressures on this problem. Okay, and we're not going to have a delta P over Q. We're going to have more, for plotting purposes right now, we're just going to have pseudo pressure. And we're only going to look at our first data plot. I'm just going to get us started here. Here's our drawdown data. I want to start it with collapse these up. Applying pseudo pressure instead of PA. I don't know why I did that. I don't need this column. Let's see if we can get our derivative plot up there. That's okay. dP, the log of t. I don't know why I can't get my scale. What happened to my data? Just kind of floundering around here trying to get a start. Okay, here's my derivative. I can plot that at time average if I want to. How come I don't have it? I don't need that number. That's during my flow time, 0.75 to 1 hour is my first one. I'm not using PI. I should draw a line like this. Okay, that's time zero, that's initial pressure, same thing we got over there. Now I'm just doing the average of those two, and this should be the derivative of those four. Okay. And those should be plotted against each other. derivative. And you see how I got my y numbers down there? If I want to move them over here, I can change them so that my, where they cross is at, instead of 1 is 0.1. I lose those things. Be sure of curious. All right, that's a good place to stop. I got my data plotted. And you know that we're going to do a slope and an intercept, and we're going to use a permeability equation, except for in our tables, we have an equation for utilizing pseudopressure. I got it in my PowerPoint. Using adjusted variables, here's the equation we have been using right here. And if we use pseudo pressure, we're going to use this equation for perm, 1637 QT over MH. That's different than this 162.6 Q. We lose the B sub G and we lose the mu sub G because we're using pseudo pressure. So we're going to use this equation right here to calculate perm. So table 6.1, gas using pseudo pressure and time. So proceed, and you guys should be able to come to class with answers for permanent skin. Wellbore radius, radius of investigation, and the amount of gas investigated. And of course, you have the permanent skin to compare with the textbooks, but you may use a different equation, you use pseudo pressure. And we'll pick up there next week. Yeah. But an M of P versus the semi-log of time. Pseudo pressure versus the semi-log of time. I plotted average time versus the semi-log derivative. Is what?
Point 9, the column that starts with point 9.
No, it's previous, it's from the previous columns.
Okay.
It's if I'm taking the derivative between 2 points, I'm plotting it at the average time. Okay, because I can't, instead of plotting it there or here, I'm plotting it at the average time. It really doesn't make too much difference. You see, I can actually plot it versus real time if I want to. It doesn't really make a lot of difference. It's slightly more accurate if I'm trying to select data. It certainly doesn't change the shape of the plot. It just centers it a little bit different. If I had a really good horizontal line and then it broke wrong, it might help me decide exactly where to start using the data.
So what is the point 9? So how did you get those numbers?
It's the average.
Oh, yeah. Okay.
Yes,
column, how do you get it?
The F column is the seminal derivative. So that's the data that's supposed to be here horizontal. While we're goofing around, I can use this one too. This will give me, this will smooth my data a little bit. I thought it would. Yeah, smooth my data. I'll have to explain that at the beginning of the next class.
Excuse me, can you put it again in the negative always? Yeah.
You're not getting the same numbers in that column, the numbers you get.
And then I just copy paste the numbers in from when I did the problem last year. Are my numbers wrong? My input data?
The column F,
Column A?
column F.
Yeah.
I'm getting the same thing.
What about it?
I'm not getting the same numbers. I've done this.
Is your MP the same?